Recording in progress.
All right, so welcome everyone to the Schubert seminar. We're very happy to have you join. So today we're gonna have Neil Fan from Sichuan University telling us about Bumpless pipe dream fragments, equivariant geometry of clans. So please take it away, Neil.
Okay, I thank you for the invitation. I'm very pleased to speak at the Schubert seminar. I will turn off the camera. Okay. Today I will talk about two combinatorial structures arise naturally from the study of k-orbit closures. One is Bumpless pipe dream fragments, looks like this, and the other is clamps. We will see in a few minutes. This is based on joint work with Yiming Chen, Xiong, and Ming. This is the outline of my talk. I will first introduce some backgrounds on symmetric pairs, and then introduce the combinatorics of clamps and our main result of Bumpless pipe dream fragments and some applications. Let us start with some theoretic background. A symmetric pair is a pair GK, where K is the fixed point subgroup for some involution theta on a reductive group G. When G is GLN, there are three types of symmetric pairs. Type A1 is the involution is first take transpose and then take inverse. And the fixed point subgroup of this involution is just the orthogonal group ON, because the ON consists of exactly the matrices whose transpose equals its inverse. For type A2, we can obtain the fixed point subgroup, the symplectic group SP2M, by using transpose of the J2M. And type A3, we use IPQ as a conjugation, and the fixed point subgroup is GLP cross GLQ. So this is three classical types of fixed point symmetric pairs. Symmetric pairs arises from the study of real groups. Each symmetric pair GK correspond to a real form of G. For G equals GLN in type A1, the corresponding real form of G is GLN of R, the general linear group over the real numbers. For type A2, the corresponding real form of G is GLM of H, the general linear group over quaternion numbers. And for type A3, the corresponding real form of G is the pseudo-unitary group U of PQ. This frameworks enables the translation of real questions into complex settings. For example, the geometry of k-orbit closures over Frag varieties is closely related to the representation of real groups, say Vogan and Lustig Vogan. Symmetric pairs is an important example of spherical subgroups. A subgroup H of G is called spherical if its action on the Frag variety G over B has a finite number of orbits. That is, the H orbits of GB is finite. The most classical example is the Borel subgroup B itself, which is spherical. The classical Brohat decomposition gives a bijection of the B orbits over on G over B with the Weyl group. Each B orbit is a Schubert cell. For a symmetric pair GK, the subgroup K is also spherical. So we want to study the K orbits of K on G over B. When G is GLN, the flag variety G over B is the space of complete flags. Each flag is a nested sequence of subspaces of Cn, and the G over B admits a GLN action by changing basis. So the indexing set of the K orbits are as follows. For type A1, the indexing set is just the set of involutions in the symmetric group Sn. For type A2, the indexing set of the K orbits are the set of fixed point free involutions. And for type A3, the indexing set are PQ clams. We will focus on type A3. So what is a PQ clam? Is my second part. A PQ clam is a partial matching on P plus Q nodes with unmatched nodes cornered by plus or minus signs, such that the number of plus signs minus the number of minus signs equals P minus Q. For example, this is a clam. There are 6 nodes, and the number of plus signs minus the number of minus signs is 0. So P equals 3 and Q equals 3. This is a 3-3 clam. We can define 2 permutations, U gamma and V gamma, for each clam gamma as follows. To define V gamma, we first label the left endpoints or plus signs from left to right. Say this is our left endpoint, this is our left endpoint, and this is a plus sign. And then we label the right endpoints or minus signs from left to right. So we label the minus signs and the right endpoints and right endpoints. So V gamma is the labeling of the nodes, which is 1, 4, 2, 5, 6, 3. Similarly, we can define U gamma. Just switch the plus signs and the minus signs. So we first label left ends or minus signs. Then we label right ends or plus signs. So in this case, U gamma is just 1, 2, 3, 4, 5, 6, because left endpoints, minus signs, left endpoints. It's the definition of U gamma is important. We will use this several times later. So just remember, we first label the left endpoints and the plus signs, and then label the minus signs and the right endpoints. So how each clam index K orbit. For a clam, we construct a flag, capital V dot, as follows. We use a matrix gamma dot to represent the flag. We use the columns of this matrix gamma dot to span the subspaces. So the column vector little vi is as follows. Little vi is either a standard basis vector or the sum of 2 standard basis vectors. If the node I of gamma is either a plus sign or minus sign or right endpoint, then vi is a standard basis vector, which is E sub V gamma of I. If the node I of gamma is a left endpoint, then Vi is the sum of 2 basis vectors, that is E sub V gamma of I plus E sub V gamma of J. So there is only one situation. The Vi is the sum of 2 standard basis vectors, that is the left endpoint. So for this case, for example, for this node 1, it's a left endpoint, and it is matched with the 4th node. V gamma 1 is 1. V gamma 4 is 5. So the first vector of gamma dot is E1 plus E5. Similarly, for this left endpoint, V gamma 3 of V gamma of 3 is 2, V gamma 5 is 6. So this vector is E2 plus E6. This is here. So we for each gamma, we constructed a matrix gamma dot. And this gamma dot is a point in its orbit. It's in its k orbit. So we use Y gamma circle as the k orbit of gamma dot. And we use Y gamma to be the closure of Y gamma circle. We aim to study the equivariant cohomological class of V gamma sub t. So we want to study the cohomological class, such as the polynomial representative of this class, like the classical case. There is the most simplest case for which is P equals Q equals 1. In this case, K, the spherical subgroup K is GL1 cross GL1, which is just the diagonal matrix AB. AB are both A and B are non-zero. And the fragment G over B is just the pseudo, the projective lines P1. So there are three orbits. Correspond to the three clamps here. For this clamp, for example, for this clamp, plus sign followed by a minus sign, V gamma is the identity because we label first the left endpoints or plus signs. So V gamma is identity, and there is no arc. So gamma dot, the matrix gamma dot is the identity. So the k orbit of gamma dot is the product of this. So the first vector is A0. The first column is A0. It's exactly the x-axis, and which is the point 0 in P1. For this case, there is an arc connecting the two nodes. V gamma is still the identity because we first label the left endpoints. So V gamma is identity, but there is the first vector, the first column of gamma dot is 1, 1 because there is an arc. So the first column of k orbit is AB, where A and B are both not equal to 0. So this is just the lines which are not equal to the x-axis and the y-axis. This is the open orbit. And finally, for this case, V gamma is 2, 1 because we label the left endpoints or plus first. So this is 2. This is 1. This is 2. The V gamma is 2, 1. So the corresponding matrix is this. So this is the y-axis. This is the simplest case, the k orbits indexed by clamps. There are three special types of clamps we care about. First is the matchless clamp. There is no arc. Just these clamps correspond to closed k orbits. Apparently, there are P plus Q choose P many k orbits, and the second special clamp is a rainbow. This corresponds to the unique open orbit. A rainbow is constructed as follows. We just connect the first node with the last node, the second node with the second last node, the third node with the third last node, etc. And the remaining unmatched nodes in the middle all have the same thing, all have the same sign. It's a rainbow. And another special types of clamp is long crossing clamp. Just the arcs do not cross each other. This indicates the orbit closures are Richardson varieties. So we want to study the polynomial representative of the orbit closures. By Borel, the cohomological the equivariant cohomology class, cohomology ring of G over B is the quotient ring. Is this quotient ring? So we want to find a polynomial representative of Y gamma sub T. For the classical case, the Schubert class, that is B orbital closures, the class of B orbital closures are represented by double Schubert polynomials of Lascaux and Susenberger. The representative of the cohomology class of type A3 orbit closures are determined by Wyser and Yong in 2014. So we will recall the definition of Wyser and Yong of their polynomial representative. Their polynomial are called upsilon gamma. Recall that this is the divided difference operator acting on a polynomial, and the super polynomials are defined recursively as follows. There is a starting point, W naught. This is a product of these factors, and the induction steps are using the difference divided difference operators. The definition of upsilon gamma of Wyser and Yong are similarly. If gamma is non-crossing, then upsilon gamma is the product of two Schubert polynomials indexed by V gamma and U gamma. Here, the Y variables in U gamma are reversed. If gamma is not non-crossing, we use the divided difference operators to apply on act on upsilon gamma. So we need to explain what is Si star gamma. This is essentially defines a weak order, like the weak order on permutations, weaker order on permutations. So we want to define the action of Si star gamma. So we first need to recall the length of a climb. It is essentially the dimension of the orbit closure Y gamma, but it admits a combinatorial description. So the length of gamma is the sum of distance of the arcs. For example, Ij is a matching. There's an arc between I and J. So this is the distance of the arc minus the number of crossings in gamma. So this is the length of gamma. So there is a neo-Hecke algebra action on climbs. There are 6 cases. For instance, for this case, the action of Si on gamma is just to interchange the 2 adjacent nodes. For example, for this case, a plus sign followed by a minus sign, or minus sign followed by a plus sign. We just add an arc. You can see that the length of the climb increased by 1 because the length of this is 0. No arcs, no crossing. So the length is 0. If we adding an arc on these 2 nodes, the length increased by 1. Similarly, for these 2 cases, if there is a sign and an arc which are adjacent, we can move the sign under the arc. These 2 cases. You can see that the length also increased by 1 because the distance of this arc increased by 1 and the crossings are not changed. Similarly, for this case, if there are 2 arcs adjacent to each other, we can make them cross. This increase the length by 1. There's a crossing more, adding a crossing more, but the distance of the arcs increased by 2. So, and similarly, these 2 situations, if there's a crossing around 2 adjacent nodes, we can make in a nesting. We can make into a nesting. So these 2 cases. it's easy to see that the length increased by 1. So this defines the weak order on clamps. There is also a strong order defined by inclusion of orbit closures. So this is an example of all the Hasse diagram of all 2-2 clamps. The dashed lines indicate strong order. So you can see that the matchless clamps have length 0, and the rainbow has the maximum length. It's unique. Generally speaking, roughly speaking, the Neo-Hack algebra action wants to make to transform each clamp into a rainbow. Wants to make each clamp into a rainbow. So the well-definedness of upsilon gamma. For the Schubert polynomials, there is only one starting point, W naught. It's a product of factors. The well-definedness of Schubert polynomials is dependent on the fact that the divided difference operators satisfy the Bride relation. But for the upsilon gamma, for the clamp, the weak order on clamp, we have different choices of the starting point. For example, if we want to compute the upsilon gamma for this clamp, we can choose. We have several choices, starting from any of the following 3 matchless clamps and by any passes. Wyser and Yong show that it's independent of the choices of the starting point and the passes on weak order. So it's well defined. I think it's a good time to take a break.
Yes, very good. Thank you very much. Yeah, let's take a break. Let's say until 4 minutes, until 4:57.